Hello everyone. So let's continue the discussion of non-negative measurable functions, the Lebesgue integral of non-negative measurable functions. So in the previous class we discussed about Fatou's lemma and monotonic convergence theorem. Now let's continue the discussion. To start with, let us see a proposition. Suppose if f is a non-negative function which is integrable over a measurable set E. In the previous class, we learned that an integral of f over E, if it is less than infinity, if it is finite, then it is integrable over a measurable set E. Then, for given epsilon greater than 0, there exists a delta greater than 0 such that for every set A, which is subset of E with measure of A less than delta, we have integral of f over A is less than epsilon. We have to show this. Okay, let's prove this. Now, since your f is a non-negative function which is integrable over E, your f may be bounded or may not be bounded. So let us prove for both the case this result is true. First, suppose that f is a bounded function. Then we knew by the definition of boundedness of a function, there exists some positive integer, say m, such that 0 less than or equal to f of x less than or equal to m. Because your f is non-negative function, this has to be true. 0 less than or equal to f of x. And this is less than or equal to some m. Now they are given epsilon is greater than 0. So given epsilon greater than 0, assume that delta is some epsilon by m. Because m is positive, epsilon is also positive. We can assume this. So your delta is also greater than 0. And suppose if there is a set A which is subset of E with measure of A less than delta, then integral of f over A is less than or equal to, because your f is less than or equal to m, I can write this one as this is less than or equal to integral of m over A. Because m is a constant, I can take it out. If you take this one out, then this is m into integral of 1 over A, and integral of 1 over A is measure of A. So m into measure of A, but your measure of A is less than delta, so m into delta, but your delta is epsilon by m. If you substitute it, then mm get cancels. So this is epsilon. Therefore, integral of f over A is less than epsilon. So in the first case, when f is bounded, we have proved the result. Now let us see for second case. Suppose that f is not bounded. That means we cannot obtain a bounded. But remember, your f of x is always greater than or equal to 0 because it is non-negative function. So only thing, we have to see the upper bound. For each positive integer n, let us construct the sequence of functions fn, where fn is defined by f of x if f of x is less than or equal to n. So fn tends to f of x if f of x is bounded by some positive integer n. If it is not bounded, then your fn of x is n otherwise. So we have constructed a non-negative monotonically increasing sequence of measurable functions such that your fn of x tends to f of x for each x belongs to E. But we know by monotonic convergence theorem that integral of f over E is same as limit as n tends to infinity integral of fn over E. So by that, let us assume that epsilon is greater than 0. Then there exists some positive integer n such that the absolute value of integral of f over E minus integral of fn over E is less than some epsilon by 2 for all n greater than or equal to n. This is by the definition of limit. Then now consider, see if so this result is true for all n greater than or equal to n. So if you put n equal to n, then this result becomes integral of f minus f integral of f over e minus integral f n, capital N, over e is less than epsilon by 2. But this can be written as integral of f minus fn, and no need of this modulus because your fn tends to f. So this is less than epsilon by 2. Now choose delta as epsilon by 2n. Epsilon is also positive, n is positive, therefore this we can assume this value. And suppose if there is a set A which is subset of E with measure of A less than delta, then what is your integral? F over A. This we can write as integral of f minus fn over A plus integral fn over A. But remember, because your A is subset of E, your integral f minus fn over A is less than or equal to integral f over E. We are going to replace that. So f minus fn over E plus integral of fn over E. But integral of f minus fn is less than epsilon by 2. So this is epsilon by 2 plus, what about this? You should note that this is n times measure of A. This we have learned that one from the previous result. There we have proved that integral of fn over A is less than n times measure of A. So because of that reason, fn integral sum of these two is less than epsilon by 2 plus n times measure of A. That is epsilon by 2 plus n into, what is your measure of A? Your measure of A is less than delta, but delta is epsilon by 2n. So if you replace this and cancel off these two, you will get epsilon. So in both the case, we have proved the integral of f over A is less than epsilon, and this completes the proof. Now let's move on to the general Lebesgue integral. So let us define two definitions. First one is, we mean a positive part of a function is f plus of x, which is maximum of f of x and 0. This is positive. This is called as positive part of a function f, and the negative part of a function f is denoted by the symbol f minus, which is f minus of x, which is maximum of minus f of x and 0. And note that if your f is measurable, then f plus and f minus both are measurable. And further, your f is nothing but f plus minus f minus. And modulus of f is f plus plus f minus. So these are some simple conditions. And a measurable function f is said to be integrable over E if both f plus and f minus are integrable. Therefore, integral of f over E is integral of f plus over E minus integral f minus over E by this. I had given exercise. You just work it out. These are simple. Now let's move on to next theorem. What is Lebay convergence theorem? The statement is, suppose if G is integrable over E and if there is a sequence of measurable functions satisfying this condition, that is, each fn is bounded by G on E, and for almost all x in E we have limit as n tends to infinity fn of x is f of x, then we have to show that limit of integral fn over E is f over E. Now let us consider the function G minus fn. Remember, your fn is bounded by G, therefore G minus fn is non-negative measurable function. And your fn converges to f almost everywhere. Therefore, your G minus fn converges to G minus f almost everywhere on E. Therefore, by Fatou's lemma, integral of g minus f over e is less than or equal to limit inferior of g minus fn over e. And remember, your mod fn is less than or equal to g and fn converges to f. Therefore, mod f less than or equal to g and g is integrable. Therefore, f is also integrable. And also we have integral of g minus f over e, which is same as integral of g over e minus integral f over e by these results, which is less than or equal to integral g minus, if you multiply this limit inferior by minus sign, that becomes limit superior. So limit superior of integral of fn as n tends to infinity over e. Upon multiplication by minus sign on both sides, this inequality get reverses and we get limit superior as n tends to infinity integral fn is less than or equal to integral of f over e. And let's call this one as 1. Similar to this, if we consider g plus fn, we can prove that integral of f over e is less than or equal to limit inferior of n tends to infinity fn over e. Here this is less than or equal to this and limit superior is less than or equal to integral of f. So these two implies that this is possible only if integral of f over e is equal to limit as n tends to infinity integral fn over e. And this completes the proof. Thank you.